Okay, this is task number 4. यहाँ पर हम we will do serial matrix multiplication first. Then after that, by using OpenMP, we will run this in parallel. Rather than that, in theory we have discussed speed up. So we will calculate cost, efficiency, and at last we will compare the answers to check. Initially we will focus on the matrix multiplication function. We have two identical functions. The first one, matmul, is normal serial function, and the matmul OMP is designed for parallel execution concept. Both codes are same, but we only used a parallel block of pragma over here, as well as the for loop pragma block, while the technique and code is same. So there we have three variables applying on the square matrix. So I and j are rows and columns, and k will define the kth element, keeping in view the concept of multiplication rows to columns. So this first for loop will iterate on the rows of A matrix, and another loop will iterate on the columns of the B matrix. Then we will define a variable dot, where we will store the result of the dot product, as the third loop is computing the dot product. Now let's see this part of the code. In C or C++, we store the arrays in one dimension. So we will go in this way, in this method. What we are doing in these two steps, this part will escape the rows of matrix A, and after adding will reach to that element whose dot product need to be taken out. This part is iterating the matrix B's column, that is B's k into n part, and as soon as it will get the required column, and then after skipping these number of columns, it will pick up the required element. Then finally the selected two elements will get the dot product and will store the result in dot variable. We will repeat the same scenario over here as well. We will do this practice here as well, as this will stored in one dimension. So we will skip these rows and the number of columns need to be skipped. So we will write it accordingly over here. This is J. So what I was trying to tell you, that current row into total columns will add finally to the current column, and final value will stored into C respective element. So working of both the matrix is same. Now let's discuss the main function, where we have defined these variables. I for iteration, integer n is actually discussing the size of n by n matrix. We have initially taken it as 500. So we have also tested it on 2 and 10. The value was not coming as proper. So as per our experiences, I've put the value 500, and you may also take it as 1000. So you may test on 500 and 1000 for getting the best values. And more than 1000, obviously the calculation will take more time. So obviously you will not get your results appropriately. So obviously your this program will become hardware dependent. So that's why I'm saying taking the values till 500. After that, we have initialized 3 pointers. You have already expertise of pointers in programming language. So we will going to use them for memory allocation. You can see the code here, where our matrices will going to store. And after that, these are some variables for the time. One for starting time, one for serial time, means how much time taken in serial execution and how much time taken in parallel execution. And then we have these results. Obviously you will get this formula in theory as well, means how was our speed up, what's the amount of efficiency, what's the cost of serial, and what's the cost of parallel. At last we will compare the cost of serial and cost of parallel, so we can say that whether the benefit arrived in parallel or not. Int p are basically our number of processors. Obviously total number of threads would be part of it. I've also done the testing of it. I've already told that by default there are 12 threads in my PC, and I'm getting proper results on 2, 4 and 6. And after that, if I'm going to increase the number of threads more, then I was getting all the threads remaining as idle. As you all know that it takes time to allocate the memory from RAM. So mostly it assigns the task to one or more than one, you may call it as 2 threads, while the remaining threads seems idle. More than that, already told that we have done memory allocation over here. So we have done a breakdown over here to tell you all, to represent you all. You already know that this is called typecasting. That is actually we are memory allocating of type double. Otherwise memory allocation malloc will make its type default. So usually it's unknown that in which memory location we are storing it, string or integer. So here we are actually forcing to store the double in the memory location. And obviously asking the size of double means obviously you know that the size of double is 8. So it will multiply 8 bytes into n by n matrix. Let's say if we have 1000 value of n, so 1 million would be our elements in 1000 by 1000 matrix. So 1000 would going to multiply by 8, so around 8 megabytes would going to be allocated for A. So I'm talking about 1000, so 500, for 500 it would be more lesser than 1000, that is would be 4 megabyte. In this way A and B are matrices and our output would store in C, and after that this for loop, this will store the random values into the matrix A and B, and the values would be between 0 and 1. After doing this, we will apply the code of serial execution. We will set a start time value. So OMP get W time does what? It stores current time value in seconds, will store in the start time. After that, matrix multiplication serial function will call, and then when this function will execute, after that we will again call the serial time and we will store current time minus the starting time value. So in technical terms you will get the serial time actual value. Then you will print that serial time duration. Similarly, we have the parallel execution code. Then I call matrix multiplication OMP. Then I've taken out the formula of parallel time. Then we have printed out the parallel time in the similar fashion. Now at the last we are coming towards the matrix calculation of the speedup. The formula of speedup is to divide the serial time with the parallel time. So you will get the parallel time speedup. Obviously you know that speedup greater than 1 is better. Ideally it should be like that the number of threads you assigned should be closer to the value of p, that is 2. So in actual you will find that the default number of threads value whatever you have, it will come either equals to or smaller than that, as it takes time to allot the task. For that reason the time value usually increases. Efficiency formula is also given in your theory classes. It's like that, speedup divided by processors. You may consider this processor work. So speedup would be in double as time is coming in double. So we will get the efficiency. Obviously its value is in percentage. Obviously it would be in double, then we will multiply it by 100. So we can see that how efficient our system is in parallelism. Then after that we have taken out two costs. Technically the serial cost is equal to the serial time, as one process is running the whole task. Whatever the task time it will be actually the serial cost. Parallel cost means however the number of threads you need to execute, we multiply the parallel time with that. Then the output would be the cost of parallel. So actually how much resource is allocated is actually your cost of parallel. It is how much resource is consumed during this parallel process, how much resource was consumed by the serial process. At last we will print all these metrics. And finally the most important step is to free the memory locations, as a function will return 0. So here I have written a small example for the cost. If a single process is taking 10 seconds, then the serial cost would be 10 seconds. And if in parallel, if 4 processes consuming or taking 3 seconds, so obviously it needs to be executed early, as all 3 processors will do this task in parallel, but their cost is more expensive than the serial time. Technically parallel is faster, but their overall cost is more. So now let's run it on terminal. So now the output is, and you can observe the serial time is more than the parallel time, which is 0.054. In my code I have told you all that speedup is should be ideally close to the number of threads, and here we are getting our speedup as 6.46. So this seems quite abnormal. The reason is, as we are working in more memory and as the CPU cache is not having such space so that it could store every process or every matrix result. So most likely 8 MB cache. Hopefully you have the concept of L1 L2 cache. So what actually happens when the task is executing serially, CPU picks the task from the RAM, due to which the serial time actually increases. For that reason the speedup is high. Logically it should be closer or nearer to 2 or lesser to 2. So here the value is 6.46 for 2 threads. And here we are working on 500 by 500 matrix. Similarly, the efficiency should be equal to 1 or lesser than 1. It means 323% efficient. So it's look like that we are getting more work in parallel. So as we are dividing the task into the threads, so the memory of each thread would be different. And obviously it would calculate early. So if we will going to increase the size or will increase the number of threads, then obviously this efficiency will going to down, and technically the speed up value will also going to down. You will observe this and you will show the report into your workbook work. So we can also test it over here, that let me first test it for 6 threads, and if I'll run it again, that 0.395 seconds for serial time. In earlier results we got it as 0.34. So serial time increased and parallel time also changed. Right now we are also observing that parallel ones is executing early and fast. In this case the speed up have increased more. Now let's test it for 12 threads and then run the same code. Now we can observe that speed up value is now reducing and efficiency is also decreasing. So you have observed that initially in the last we got efficiency 1.18, that is 118%. Now efficiency with the increase of the processors have been decreased to 48%. Now what actually happening that in most of the time in parallel computing, our threads are in waiting state for the processors, that when we will get the data then we will start processing. So this is the decline of efficiency. And the speed up is still more. The reason is as we are working on the huge data size, so serial will obviously having the greater value when you have a big data size. So now let's do what? Change the size of the n, that is matrix size. Also change back the process size to 2. Now let's test it. Now you are viewing that serial time is 0.003 and parallel time is 0.002. Now you are observing that in serial we are getting the faster execution as the size have been reduced. So now speed up is all around 1.5, that is lesser than 2, and efficiency is 75%. So now let's retest with the same size and set the number of threads as 4. Now we are observing that speed up is 3, results are almost similar, that is 0.003 and 0.001. Efficiency is still 75%, but you are observing that in last 2 consecutive cases the cost is very smaller, that is approx equals to 0 as the data size reduced. The answer is coming in points and it's actually rounding it off. Now let's change the size of n to 1000 and take processes threads as 2 and now run the code. So now you can see that the number of processes increased, so it's taking time. You can see that serial again jumped to high value, that is 3.18 seconds, as processor needs to take a lot of data from the RAM. With this cost, speed up value have also enhanced and efficiency also increased. But with that, we have to expend a lot of cost. So with varying these results, we can observe many things, but the main issue is that in C, we are actually making the 1D storage as in C variable, plus the memory allocations are having high value, especially when you increase the number of n. So it all depends on what our value of n is and how many number of threads we are taking. So you may also write in your workbook after this presentation of mine that why these values are reflecting different values, different results. Means if we have high order, the serial time would obviously more, as the CPU cache that assigns to that respective thread is not as high, is actually smaller. So if our data is having more value than cache memory, then obviously it will take the help from the RAM for memory allocations. Due to this reason, the serial time of ours is very slow. Okay students,